Hello everyone. Imagine this, by the late 1800s physicists thought light was completely understood. It was described beautifully as a wave, explaining interference, diffraction, and polarization. But something strange happened. The photoelectric effect refused to obey wave theory. According to the wave picture, light's energy is spread smoothly over the wavefront. So, if we increase brightness or intensity, electrons should gradually absorb more energy and then escape from the metal surface. But the experiments told a different story. Electrons were emitted instantly, with no delay, and their energy depended not on brightness but on the frequency of the light. Let's look at the four major contradictions between wave theory and what nature actually showed us. First, wave theory predicted that higher intensity means higher energy for each electron. But experiments showed the electron's energy depends only on frequency, not on brightness. Second, wave theory said any light, if intense enough, should cause emission. But in reality, no electrons were emitted below a certain minimum frequency, known as the threshold frequency. Third, wave theory suggested that electrons would need time to absorb energy before escaping, but photoemission happened instantly, within less than a billionth of a second. And fourth, wave theory assumed light's energy was shared among all electrons, yet only a few electrons got the right amount of energy to escape. In 1905, Albert Einstein proposed a bold idea that completely transformed physics. He said light is not continuous, it comes in tiny packets of energy called photons. Each photon carries a discrete amount of energy, given by the equation E equals h times nu. Let me repeat that. E is equal to h times nu, where E is the energy of one photon, h is Planck's constant, which equals 6.626 times 10 raised to the power minus 34 joule-second, and nu is the frequency of light in hertz. That means a beam of light is actually a stream of photons, each photon transferring its full energy to a single electron during collision. Einstein then applied this photon concept to the photoelectric effect. When a photon hits a metal surface, its energy is divided into two parts. One part helps the electron break free from the metal's surface. That energy is called the work function, represented by the Greek letter phi naught. The remaining energy becomes the kinetic energy of the emitted electron. This gives us Einstein's famous photoelectric equation, nu equals phi naught plus k max. Spoken fully, Planck's constant h multiplied by frequency nu equals work function phi naught plus maximum kinetic energy k max. We can rearrange it as k max equals h nu minus phi naught. That is, the maximum kinetic energy equals Planck's constant h multiplied by frequency nu minus the work function phi naught. Only if the photon's energy, h times nu, is greater than or equal to the work function phi naught, can the electron escape. Otherwise, there is no emission, no matter how bright the light. This simple equation explained every experimental result perfectly. Observation 1. The maximum kinetic energy of electrons increases linearly with frequency, exactly as predicted by the term h times nu minus phi naught. Observation 2. No emission occurs below a minimum or threshold frequency because h times nu is less than phi naught. Observation 3. Emission is instantaneous because a single photon transfers its entire energy to a single electron, no time delay at all. Observation 4. The energy of emitted electrons is independent of intensity because intensity only changes the number of photons, not the energy per photon. So, Einstein's equation h nu equals phi naught plus k max unified all observations in one stroke, an achievement that completely reshaped modern physics. Let's now visualize this equation. From k max equals h nu minus phi naught, We know that if we plot the maximum kinetic energy on the vertical axis and the frequency on the horizontal axis, we'll get a straight line. If we instead express kinetic energy in terms of the stopping potential, we can write EV0 equals h0 minus phi0. Let's speak that clearly. Electron charge E multiplied by stopping potential V0 equals Planck's constant h multiplied by frequency nu minus the work function phi0. In this graph, the slope of the line is Planck's constant h. The x-intercept represents the threshold frequency nu naught. The y-intercept corresponds to minus phi0 divided by E. Let's apply this equation in a simple example. Suppose a metal has a work function phi0 of 2.0 electron volts. We want to find its threshold frequency. We know phi0 equals h times nu naught. So, nu naught equals phi0 divided by h. Now substitute the values. Nu naught equals open bracket 2.0 times 1.602 times 10 raised to the power minus 19 close bracket divided by open bracket 6.626 times 10 raised to the power minus 34 close bracket. When you solve, you get nu naught equals 4.83 times 10 raised to the power 14 Hz. This means that only light with frequency above 4.83 times 10 to the power 14 Hz, roughly violet or ultraviolet light, will cause photoemission. Now let's find the energy of a photon with wavelength 500 nanometers. We use the relation E equals hc divided by lambda. Speaking that fully, energy E equals Planck's constant h multiplied by speed of light c divided by wavelength lambda. Substitute E equals open bracket 6.626 times 10 raised to the power minus 34 close bracket multiplied by open bracket 3 times 10 to the power 8 close bracket divided by open bracket 500 times 10 to the power minus 9 close bracket. That gives E equals 3.97 times 10 to the power minus 19 joules, which equals 2.48 electron volts. So a photon of green light carries about 2.48 electron volts of energy, just enough to liberate electrons from some metals, but not all. To wrap up, let's summarize the beautiful simplicity of Einstein's idea. Each photon of light carries energy equal to h times nu, Planck's constant multiplied by frequency. When that photon hits a metal surface, the energy splits. Part of it goes into overcoming the work function phi0, and the remainder becomes the kinetic energy of the emitted electron, given by K max equals h nu minus phi0. This equation, h nu equals phi0 plus K max, explained all the puzzling results that the wave theory failed to describe. It marked the beginning of quantum mechanics, introducing the revolutionary idea that light, and later even matter, has both wave and particle nature. Einstein's explanation of the photoelectric effect earned him the Nobel Prize in Physics in 1921, not for relativity, but for this breakthrough.